Hello and welcome. I'm happy to welcome all of you back, and we're finally on to topic 4.1 global and local extrema of a function. So, you may recall from the last chapter that for the most part, what we've been doing so far is computing derivatives. However, the really cool thing about this entire chapter is it's going to be focusing on the application. And one of the most important parts of application is being or finding maximums or minimum or really optimizing things. And that's going to be one of these very important ideas in calculus. So we're starting this off with how do we actually find these global and local extrema of a function, and that's really what these first 3 videos are going to be on, if I remember correctly. Something like that. Yeah, something about the first 3. And we're also going to be going over graphing, Newton's method, and so much more in this chapter. But let's get into this. So to start out, I think it's always important to review our basic skills. So for this first function here, we need to take the derivative of this with respect to x. We get the derivative of y with respect to x is equal to... Well, actually, before I do that, I want to use some exponent or logarithm properties here. So I get y is equal to the natural log of 2 plus 2 times by the natural log of x. Now taking the derivative of this is a bit easier of a derivative than this to compute. All we get is 2 over x as her answer. All right. For our dy dx. All right. And we also want to find the second derivative. So we know dy dx is really just 2 times by x to the negative 1. So then the second derivative of y with respect to x is equal to negative 2 times by x to the power of negative 2, just using the power rule. And that, my friends, is our answer. There we go. All right, now on to tangent inverse of 3x. All right, so tangent has a derivative, and I can't do any simplification of this. So dy dx here is going to be 1 over 1 plus 3x squared times by the derivative of the inside, which is 3. So we get dy dx is equal to 3 over 1 plus 9x squared. Now what we're going to do is we're going to rewrite this to make this easier to differentiate. So we get 3 times by 1 plus 9 over x squared to the negative 1. Now this looks just like a channel derivative, so taking the derivative with respect to x, we get the second derivative of y with respect to x over dx squared is going to be equal to negative 3, because we bring the power down, times by 1 plus 9x squared to the negative 2, times by the derivative of the inside, which is just 18x. So we get the final answer here. Well, 3 times by 18, 3 times by 8 is 24. 3 times by 10 is 30. So we get negative 54x all over 1 plus 9x squared. And that is going to be our second derivative's answer. So where we're going to start here is global extrema. So let C be a number in the domain D of a function f. Then f of C is, well, it would be an absolute maximum if f of C is greater than all other values of f of x. However, it will be an absolute minimum if the values of c are going to be less than f of x for all values of x. So in the following graph, I want us to look at the shape of the graph and determine where are these maximums and the minimums. And it's important to note that these maximums are going to be given as a y value, or these global extrema. So I suppose I should have marked this down as f of a, f of b, and finally we have f of c. Alright. Well, we can clearly see that this point f of b is going to be the maximum, as there is no other y values that are as tall as it. So we have the global max is y is equal to f of b. Well, let's find the global minimum now. Well, we look at all the points. This f of c looks to be maybe that global minimum. We see are all other values of f of x higher than f of c, and we see that is true, so we get an answer of y is equal to f of c is our global minimum. Moving on, we now have to be a bit more specific here, as we now also have to deal with local extrema. So what is the difference? Well, the number f of c is a local maximum if f is, that's supposed to be an if, not an it. But the number f of c is a local maximum value of f if f of c is greater than f of x when x is near c. F of c is a local minimum value of f if f of c is less than or equal to f of x when x is near c. Find all the relative and maximum extrema for the following graph. So, interestingly enough, I just want to talk us through this. So the difference between a maximum extrema is it's for the entire interval. It's going to be the highest value over the entire interval. However, many functions will often have areas that are higher than the rest or lower than the rest. And these two are extremas in many cases. So, whenever defining it this way, what we want to do is we want to be looking for at each of these values here. And let's say we're looking here at x is equal to a. Well, is the values around a here greater than a? Well, yes, they are kind of greater than a. Are they less than a? Well, there's also values less than a. So even though a here has a slope of 0, which we're going to talk about here in just a moment, it is not a local maximum or a minimum. Looking at x is equal to b now, well, around b, we can clearly see that there is no value greater than b. So we know that there's a local max at b, comma, f of b. And I suppose we want to find all relative maximum and maximum extrema for the following graph. So we'll do the absolute in a moment. Now coming over here to c, looking at x values close to c, we can see that c is clearly the lowest point. So it will be a local min at c, comma, f of c. Looking at d now, we have another local maximum because there is no other value of x close by that is is greater than f of d. So we get d f of d as another local maximum. Looking now at E, we can clearly see that there is no value of f of x that even comes close to how small E is. So we get the minimum, or another local minimum, is E f of E. Now, interestingly enough, we're going to see a lot of these same values come up whenever we're doing the absolute maximum, or the maximum extrema, the global extrema. I suppose this was supposed to say global, not maximum. I'm sorry. Global. So now for global extrema, we can look at this graph, and we can see here that this value for b, f of b, is taller than, or is greater than the rest of the graph. So y is equal to f of b is a maximum. We can also see that a minimum here is e comma f of e, because all other values of the graph are greater than it. So y is equal to f of b, or sorry, f of e is going to be the minimum. And that's how we do that using graphs. So now we have the extreme value theorem. And what the extreme value theorem supposes is if f is continuous on the closed interval a to b, then f attains a absolute maximum value, f of c, and an absolute minimum value, f of d, at some number c and d in the interval a to b. So what I want us to do is just label the absolute min and the absolute max in the following graphs. So looking at this graph over here, we can tell that there's an absolute maximum at this point right here, this high point. So we are going to call this maximum c, f of c. And then now we're going to come down over here to this minimum. It kind of looks like it may not be the minimum, but I think it's supposed to be. So we're going to call this point d, f of d, and that would be our answer for this first one. Now for the second one, we can clearly see that there is a maximum up here at the value c, f of c. However, we don't seemingly have a minimum. However, we need to look at our endpoints as well, as they can also be the minimum. And you'll see that this value b is also going to be our value d, so this is going to be our d, f of d for answer. Finally now, we're going to be looking at critical points. So a critical point is a point on the graph f such that f prime of c is 0 or undefined. It is this point on the local min or max, then c, f of c is a critical point. If not, then it's useless. That is my own terminology. So, we're going to start out by taking the derivative of these functions. So we get the derivative. So we get dy dx is equal to 2x plus 4. Alright. Well, now if we want the critical point of this, we need to set this to 0. So we get 2x plus 4 is equal to 0. Solving for x, we get 2x or is equal to negative 4. So x is equal to negative 2 as our critical point. or as our possible critical point. So now I'll give you a moment to try and do the second one on your own. I'll wait. Okay, gonna get started. So we get dy dx is going to be equal to 4, negative 4, sorry, sine of 4x. And that is going to be equal to 0. So this 4x doesn't actually matter, so we just get sine of 4x is equal to 0. Then we have to take the sine inverse of both sides. So what we're going to get on this left side, and because I want all solutions for this function here, I am going to say that we are going to get values of 0 plus or minus pi n times. And that is equal to 4x. Alright. Now we just have to divide both sides by 4. And we get plus or minus n pi over 4 for our answer. And that will be all of the possible critical points for the function cosine. Alright. Now we need to learn about the closed interval method. So this is a way for us to find all the global maximum and minimum values of a continuous function f on a closed interval. So it starts out, we are going to find the critical points of f. So we're going to do what we just did up here. Then we are going to find all the values of f at its endpoints, and the smallest value that we find is going to be the absolute minimum. The largest value is going to be the absolute maximum in the closed interval. So what is this going to look like? Well, I got some examples laid out for you here, and I'm also going to talk about this inequality a little bit, because sometimes you can't just plug and chug. So I'll show you what we can do instead. So we have f prime of x is equal to 2x. We just take the derivative of this so we can find its possible critical points. Then we need to set the derivative equal to 0 and solve. So we just get x is equal to 0 as our critical point. Now, what we're going to do is we're going to say f of negative 1 is equal to 1. We know f of 0 is equal to 0. However, we have an issue here because the 2 is not included in the domain. So rather than plugging in 2, we're just going to take the limit as x approaches 2 of x squared, and we get the value of 4. Alright, well, because of this, we know that this 4 is, this 4 is going to be the absolute maximum, so we have a max of y is equal to 4. We have a min of y is equal to 0. And that would be our answer. Alrighty, for this next one, we have f of x is equal to cosine of t from like negative 3 pi over 2 to 3 pi over 2. Very interesting interval there. So what we start out by doing, we take the derivative, and I suppose this is supposed to be a function of t, not x. Alright, so we get negative sine of t is equal to f prime of t. So then we get 0 is equal to negative sine of t. So we get sine of t is equal to 0. So t must be equal to, well, if we're looking at all values in this interval, sine is equal to 0 when, well, at negative pi, All right, 0, and then pi. I believe that will be all values in the interval that was given. All right. Well, now that we have these critical points, we have to plug them into the original function along with the endpoints. So we have f of negative 3 pi over 2, which is going to be equal to cosine of negative 3 pi over 2. Well, if you're really looking at this, and I'm going to real quickly draw a unit circle. Okay, fine, I'll draw a unit ellipse. No, I'm not going to do that. This is going to be even more ellipse-ish. Nope, never mind, that's a perfect circle. So we're going to get negative pi over 2, negative pi, and then a negative 3 pi over 2. We are up here. Cosine is 0 there. So then we have f of negative pi, which is going to be, we're just going to go all the way back here, negative 1. F of pi, however, or sorry, not pi, but 0 is going to be equal to 1. F of pi is going to be equal to negative 1. And f of 3 pi over 2 is going to be equal to pi over 2, 2 pi over 2, 3 pi over 2. So 0. So we get the maximum. So max is equal, or sorry, max is y is equal to 1. And we can clearly see that the minimum value, the smallest value the function takes on, is going to be y is equal to negative 1. You may ask yourself, why do these values appear more than once? And that is going to happen quite often. That's why we have the existence of relative. Because sometimes the function does varying things relatively close together. And it's important for us to understand how the function fully functions. Alrighty, well, that's all I have for you. I hope you found this video informative, and if you do, please like and subscribe. And please tune into the next one where I'm going to be going over the topic of the mean value theorem.